Okay, so welcome to this session, Aerodynamics 1. Welcome everybody for people online. My name is King Martins from the University of Michigan, and I have the pleasure to introduce my own PhD student, Bernardo Pacini. He is student in my lab, co-advised with Professor Durasami in the gas lab, and he will be talking about urban air mobility. So take it away.
So it's a early session with our presentation titled Urban Air Mobility Vehicle Design with OpenFOAM. This continues on the theme of .foam that we started yesterday morning, Professor Martins' keynote, and then the tutorial in our poster session as well. As we get started, I want to acknowledge some of our collaborators. This work largely comes from the MDO lab and the CAS lab. We also work closely with Iowa State, NASA, a few of their centers, and the work is supported by the Collaborative Center for Aircraft Vehicle Design and the Genoa. So we're focused on urban air mobility. And what is urban air mobility? It's a vision to revolutionize travel in urban and rural areas. So our transportation networks, particularly in cities, are very congested. So the idea is that we could fly into these networks, travel between buildings in the air, and leave the cities, all using the airspace above cities, not only the ground transportation that is heavily congested. UAM prototypes are very complicated vehicles, and we see a couple of them here on this slide. These are 6 of the major industry players. The unifying factor here is that all of these designs have propellers. So we're particularly interested in studying this propeller wing and propeller airframe interaction on these complicated designs. The design space is quite large. You can see all of these companies come up with very different optimized designs in their opinion. So we're interested in trying to help figure out what is true of the optimum here. So our motivation is to design an efficient, safe, and quiet vehicle. We'll look at this from 4 aspects. First, we're going to look at aerodynamics. We want a vehicle that is aerodynamically efficient so it can perform while in cruise, while in hover, or while transitioning. We want to look at the structure. We want a vehicle that is very lightweight with advanced materials, but we also want it to be safe. We need it to not fail while it's carrying passengers. We'll look at acoustics. This is to make sure that the vehicle doesn't cause excess annoyance. It can't be annoying the people it's intended to actually serve. And finally, we'll look at component packaging. These vehicles are tightly coupled. As we make the aerodynamics more efficient, our fuel tank or our battery can get smaller, so our fuselage could shrink to make it more efficient. So we can carefully size our fuselage or the vehicle itself around our internal components. And what I want you to take away from this is that urban air mobility vehicles are comprised of very tightly coupled systems, and that as we design one, for example, the aerodynamics, we also need to consider how that changes the requirements of a battery pack, how that might change our propellers. So all of these disciplines are tightly coupled together. So how can we optimize all of this together? For this, we leverage multidisciplinary design optimization, MDO. We have a modular and multidisciplinary framework for coupled, discrete adjoint-based optimization. Optimizations are focused around an optimizer, and this gives us some design variables on each iteration. So this is some wing shape parameters, maybe a planform, a twist, or an airfoil shape. That geometry is fed into an aerodynamic solver. In this case, we use OpenFOAM or our variant alpha. If we're interested in coupled aerostructural analysis and optimization, we can couple that aerodynamic solver with a structural solver. So if we want to know the true displacement of a wing while in cruise, for example, we can model that by coupling an aerodynamic solver with a structural solver and compute our functions of interest, whether it's the stress and strain on a wing or it's our efficiency of the wing. If we're interested in acoustics, we can tag acoustics onto this as well as a post-processing routine to compute how much noise the vehicle is generating for observers on the ground below. And finally, this gets tied together in our packaging optimization where we look at the internal components of the entire vehicle. To do this, we need gradients. Gradients are very important for efficient optimization, and that's because of this figure here on the right of the slide. Gradient-free methods scale terribly with the number of design variables, and when we're doing this sort of multidisciplinary design optimization, we may have hundreds, if not thousands, of design variables, which would be simply prohibitive with gradient-free methods. Gradient-based analytic methods help us out here, and we've implemented a discrete adjoint with all of our codes using reverse mode differentiation. For this talk, I'm going to focus on a research model that's a NASA tilting concept vehicle. It's an 8-propeller vehicle that takes off and lands vertically in the configuration shown on the slide. For cruise flight, the wing tilts forwards, and same with the propellers on the tail, so it looks like somewhat like a regular airplane in cruise flight. So let's jump into the first section of the talk. Mixed fidelity aerostructural acoustic optimization. So what is aerostructural acoustic optimization? Let's first focus on the aerostructural part. If you're modeling propellers, wing, and the internal wing box, you need to model each one of those with some solver. So we do that using blade element momentum theory for the propeller blades, and we use that to get unsteady, low fidelity blade loads. Those blade loads are time averaged and passed into an aerodynamic solver so we can include the effects of the propellers on the float field on a wing. We take both the propeller loads and the aerodynamic loads on the wing and pass those into our structural analysis. This computes the deflection of the wing, which is passed back to move our propellers in space and deflect a wing as it's loaded. We repeat this process, passing loads and displacement back and forth until our aerodynamic and structural solvers converge to a solution. And once they've converged, we move to our aeroacoustic analysis to compute the noise per unit entirety. We're interested in design optimization, so we can introduce design variables here, and all of our codes are differentiated, so we can compute the derivatives of that function of interest with respect to the design variables. And we embed this inside an optimization. I won't go over all of the specific tools here, but I want to note that we use .foam for our OpenFOAM discrete adjoint with the row simple foam solver, RANs, and the SA turbulence model. So what is the optimization setup? We want to minimize the required power and cruise play with respect to some propeller design variables, the twist and chord distribution and the rotation rate of the propeller. And we want to look at the wing design, so the twist of the wing and the shape of the airflow sections along the wing. We impose some physical constraints, so we want the maximum sound pressure level recorded to be under 40 decibels. We say that the lift generated by the vehicle has to equal the weight of the vehicle, and the thrust has to equal the drag. So we've now trimmed the design with those constraints. And we also have a material failure constraint to make sure that wing box doesn't fail in flight. We embed our wing in a free-form deformation grid. What this grid is used for is we can twist each one of those four sections to adjust the shape of the wing along the span, and then we can also pull up in the Z direction in each one of those points to locally shape the airflow sections. The computational setup consists of a few meshes. The first is the aerodynamic mesh that is a typical unstructured mesh you'd see for an OpenFOAM case. And then we have a structural mesh that includes the wing box with the spars, ribs, and structural skin. We embed our blade element momentum theory results as time averaged actuator zones in the flow field. So these blade elements are actually in a separate simulation that then get added in as these gray cylinders as the actuator zones. So the baseline results, combining blade element momentum theory, CFD, and the finite element solver, is that we have negative thrust near the blade root and a very large positive thrust at the blade tip, which is not particularly efficient. We have spanwise variations with higher and lower loading behind the downgoing and upgoing propeller blade regions. And we have high stress near the wing root that decreases outward towards the tip, as you might expect for the structure. Now, once we've run the optimization, we see the design is quite different. The blade loading is shifted inboard towards the root, very far away from the tip. There's a strong suction peak on the wing that's shifted away from the leading edge. And those variations, you can see them more clearly in this contour plot where we have very strong lower and higher pressure behind the upgoing and downgoing propeller blade regions. The wing box is more stressed now and actually reaches our constraint value, and that again decreases outwards toward the wingtip. I want to show the spanwise variations here or the spanwise distributions because they show a big difference between the baseline and the optimized. We see that the normalized lift distribution on the top shows the variations behind the propeller that are even more significant in the optimized case. The optimized twist distribution has some oscillations towards starting at the root up towards the tip with significant decrease at the wingtip. And the thickness distribution thins both the root and the tip of the wing and actually increases the thickness behind the center two propellers. And what was great about this optimization is that we were able to optimize the design by decreasing the wing drag by 32.1%. So ultimately, this optimization reduces the required power by 17.8% and decreases the wing drag by 32.1%. Moving to our next topic. Once we've done the lower fidelity propeller modeling, we want to look at it in more detail. So propeller aerodynamic optimization with moving reference frames. High fidelity physics are important for vehicle modeling. And this is because propellers induce a very complex flow field with both axial and tangential flow components. And we need to capture waves. Capturing waves can be challenging and can be computationally expensive, even though we really need to do it to properly understand propeller design. This is a figure from NASA Ames of the same vehicle. You can see how complicated the flow field is behind the vehicle and behind the propellers. Understanding these wake structures and high-fidelity physics is crucial for detailed propellant design. Now, moving reference frames and periodicity can help improve this computational cost. So unsteady analysis is extremely expensive, and unsteady optimization is simply not possible right now. It is simply too expensive. So we use moving reference frames to simulate propeller physics with a significantly decreased cost, and we use periodicity to further lower this cost so we can simulate just one blade. So on the right side of this slide is our computational setup for this optimization, where we have a moving reference frame zone that goes around the hub and the blade, and then we have a far field surrounding it, and we only take one wedge of the actual far field because we just need that single blade instead of all 5 of them. So optimization setup is to decrease the required power with respect to propeller twist and rotational rate design variables with an imposed thrust constraint of the thrust required for cruise flight. And what we find is in this animation of the optimization, we see that the loading goes from being concentrated at the tip to more smoothed out over the blade, as you would expect from a more efficient design. So ultimately, this optimization helped us decrease the required propeller power by over 7% while now achieving that target thrust. Moving on to our last topic, combined systems packaging and aerodynamic shape optimization. So how do systems packaging and aerodynamic shape optimization work together? UAM vehicles have many components that must be packaged inside of the airframe, whether it's in the wing or the fuselage. And these components are tightly coupled, like we mentioned before. As the propeller changes, we may need less power, so we can make that battery or fuel tank smaller. So we set up a preliminary location for each of the components, and we envelope them into volumes. Anything that's next to each other in fixed size, like all of these passengers, we can put them into one large block. If there's something like a cargo area that we want to size dynamically, that becomes its own separate block that we optimize throughout the optimization. We then embed all of these volumes into the airframe in their preliminary locations, and we parameterize them so that we can allow the dynamic ones to change in size or change in location. So in this case, the blue one will be fixed in its location as it's a passenger cabin, but the red one is a cargo area that will allow it to change in size and move dynamically inside the fuselage. To do this, we need some advanced spatial integration methods. Typically, we use conventional constraints that approximate internal aspects of the model, and these are not directly simulated. So we impose some 2D thickness constraints that might approximate the size of a fuel tank, or some volume constraints that are there for the fuel tank or the structure. But these approximate constraints are not useful, are useful to simplify models, but not for coupled multidisciplinary optimization. And it's very difficult to update these constraints as you go through the optimization, especially if you don't model that internal component correctly. So instead, we use an intersection-based method where we compute the minimum distance between surfaces. So here we have surface B and surface A, and we compute that minimum distance between the two. The minimum distance between these surfaces is then aggregated and smoothed into a function that we can use for gradient-based optimization. And the component models can continuously change both A and B here throughout the optimization, and we just keep track of that minimum distance to make sure that they don't intersect. We parameterize the vehicle, again, with preformed deformation, a little bit different than the wing design here, but you can see as we tug on each one of those points, we can locally adjust the shape of the fuselage to try to change the design to a better one. Optimization problem is to minimize drag here with respect to some cargo design variables, the fuselage shape, the wing shape, and the wing twist and angle of attack of the vehicle. We have some constraints on that cargo volume and packaging requirements, as well as the trims of the lift of the vehicle has to equal the weight of the vehicle plus cargo, and some thickness of the wing and fuselage. I want to note here that the cargo can change shape, it's dynamic, and we impose a constraint on the size so we can target different mission types if a passenger needs, for example, 0.5 meter cubed of volume or 2 meters cubed of volume. So the optimization ends up forming the fuselage around volumetric constraints. So this is how the fuselage changes in shape. And you can see that the cargo is actually getting longer and lower in the fuselage as the fuselage is shaped more like an airfoil to make it more efficient. We tried a variety of constraint values for that cargo volume, ranging from 0.5 to 2 meters cubed. And we found that the design is quite different for each one of those. We can significantly reduce the drag for the smallest case, down to nearly 25% lower. And for the largest volume case, it has a harder time reducing that drag, and the design is a little bit different as that cargo pushes up against the fuselage. So we found that optimization decreases the drag by 24.7% for that smallest case and 16.1% for that biggest case. So still significant reductions for all of the cases. So design optimization with OpenFOAM is a powerful tool for UAM optimization. We showed mixed fidelity aerostructural acoustic optimization and how it can significantly improve flight performance. We showed aerodynamic optimization of propeller blades with moving reference frames and how it's a cost-effective method for propeller efficiency optimization. And we've shown combined systems packaging and aerodynamic shape optimization for notable improvement in airframe performance, considering geometric constraints. If you're interested in gradient-based optimization, help us advance these methods or aircraft design in general, you can check out our work on our website or on our GitHub. All of our tools are available and open source. What questions do you have?
Where do the organization is that always in the flight case? I think so about it the low flight cases, you not need to verify system.
Great question. So that applies to both the first two sections. Both of these we can use with different flight conditions. So our codes can be multi-point. So we can set up two separate geometries. Even if you have variable pitch, you can vary RPM, however you'd like to set it up. And then you can weigh the objective for both of them. We could do it both for this case and the blade element momentum theory case. That's in the works. I don't have them presented here, but we're looking at, for example, the hover flight condition, because that's a limiting factor on the structure in one direction. And then the cruise flight condition is a limiting factor on the structure in a different, or I guess a maneuver case, but it's two different directions on that structure. So yeah, we're looking at multi-point. We're not presenting that here yet.
I was wondering, how long process taking, and then kind of decided consider a little bit of the delta that is earlier on the process that maybe some sort of body technique for the normal ditch one of the delta methods and pretty much those that are
Absolutely. So for the first part of this presentation, the wing plus propeller coupling, we're working on that. There's what Professor Martin said yesterday, optimizers find all the mistakes in your code. They also find all the holes in low fidelity. So you can get some crazy results that aren't physical. So we don't have that working yet. That's not with OpenFOAM. That's with some BLM methods where we couple our blade element theory with BLM. But that is the idea, to get to that more quickly. For the systems packaging, I'm not sure how we would do that. Low fidelity, that's not something I've thought about.
First, and then the rest.
Sure. Yeah.
Another
But to answer the first part of your question of how expensive this is to set up, of course, I've experienced setting it up, but I would say that if I had to do this on a new vehicle, it would probably be about a week of setup time for all the different disciplines. And then the optimization runs in about 1 week on a reasonable cluster of maybe 200 cores.
In terms of platform for enabling protocol, next cycle.
I'll note that down. Thanks.
When you have the power
Yes. So this is separate from this MRF zone is entirely, or this MRF simulation is entirely separate from the fuselage simulation or the wing simulation. We do that because we need steady state analysis for optimization. Unsteady is simply too expensive. What we put together instead is, if I jump back to this optimization, is we take blade element theory and we run that unsteady to get the acoustic data that we need, the time history of the blade loads. We then time average one revolution to get the time average influence of propeller in the flow field. There's some work that shows that that actually does a pretty good job at capturing the trends that you need mostly for optimization to design that wing. And we put in a fixed radial distribution for the axial and tangential force on the flow. So you. I'm sorry. Sure, I don't have experience with mixing planes, so I can't comment on that. But yes. Yeah, and so that's what we implement here. So we have a steady state CFD simulation, even though we have some unsteady blade.